Our next topic is called empirical formulas. Sometimes you'll hear people use the term empirical data. It is the most basic data, most simplified data. It's the raw data before you do anything with it. It's kind of the same thing here. Empirical formulas are the formula of a given compound reduced to the lowest ratio of elements present. All right? With our ionic compounds, they're always in empirical formula. That's what we're looking for. But molecular compounds are sometimes much, much bigger, but we can reduce them to their empirical formula, which is how we get families of compounds in the molecular world. All right? So let me show you an example, a basic example. All right? This is a pretty common one. The molecular formula, sometimes they refer to it as the true formula, is C6H12O6. What's that one? You guys know that one, don't you? It's glucose, yeah. It's the sugar that's created in photosynthesis. All right? What can go into all three of those evenly? What's the biggest number that can go into all three of those? 6. That's right. Very good. Okay. So if we divide them all by 6, we get CH2O. This is where we get the phrase carbohydrates, because it's carbon and water. All right, we just started notes, okay? So this is where we get the phrase carbohydrates. All carbohydrates basically can be reduced to CH2O. Not exactly, because glucose is what's called a monosaccharide. It's a simple sugar. Sucrose, which is like table sugar, is actually a disaccharide. And then we can get into even bigger ones, polysaccharides and starch and stuff. So they get all these units, but if we break all the units apart and then break them down, they break down to CH2O. And again, carbohydrates, that's the stuff that gives you excess energy and stuff like that. So yeah, things like that. All right. So, do you have a phone? You want to snap a picture of it real quick so I can move on? I'm actually recording this one. If you got that, go ahead and snap it, and then you can just leave a space. Okay. Got it. All right. Thanks, buddy. Okay. All right. Okay. So when we are finding the empirical formula from data, not from a molecular formula or true formula, we have to go through some steps that we have been learning how to do that have to do with our conversions, okay? So these are really super duper important steps, so I would write these down, okay? So steps to finding empirical formula from data, all right? Find the grams of each element. Sometimes we do this during lab. Guys, with the weird schedule we have this week and next week, we aren't going to get to do that lab that I've done some years in the past. Sometimes I do, sometimes I don't. We're not going to be able to. Now, often we find it in the form of percentage makeup. If we're using a instrument called a mass spec, GC mass spec, it gives us the information in a graphical form, and we'll find it in percentages. If it gives you a percentage, what does percent mean? Per what? Per 100. So if it's percent, we just pretend we have 100 grams total, and whatever its percentage is how many grams we have of each component. Does that make sense? And we're going to do something like that, okay? The second step is then to convert those grams to moles, all right? We're going to convert the grams to moles. And some of these steps may not totally make sense if we're just looking at it, but hopefully they will as we do more, okay? And then the third step is to divide your answers, all of your answers, by whatever was the smallest. If we just have 2, it's whichever one's smaller. If we have 3, you find the smallest one, divide everything by the smallest one. This becomes our ratio of moles of the elements. And moles are just particles, so that ratio then becomes the formula. Now, it doesn't always come out even. If it doesn't come out even, and this is a sometime step, that's why I put stars by it. If it doesn't come out even, then you have to multiply it out till you get them all to whole numbers, okay? And we'll look at those. It's easier to look at and actually do these problems than to try and explain it as we go over the steps, okay? Oh, yeah. Dun, dun, dun. So 4 steps. Yes.
Wouldn't you, like if you divided by the smallest number and then you multiplied by that small number, wouldn't you get the exact same answer?
Okay, so you won't, when we say by a small number on step 4, that's a good question. I didn't realize that the way it's written, it is a little confusing. It won't be the smallest number of moles. It's going to be a small whole number. So let's say when we divide it out, one of the answers comes out to be 1. Oh, I'm going to switch over to my thing. Okay, if let's say after we divide it out, element A, when it's divided, it was the smallest one, so it comes out to be 1 because it's divided by itself. But element B, it came out to be 1.3. Okay, well, we couldn't have a formula that's A1, B 1.3 because you can't have 0.3 of an atom. So what we do is we're going to we figure out a number that we can multiply this by to get it. Generally, we say within a tenth. Sometimes we go a little higher than that. If it's raw data from a lab, we can maybe go up to like 0.2, all right? But so if I have 1 and 1.3, what if I multiply the 1.3 times 2, what do I get? What's 1.3 times 2? 2.6, still not close enough to round. If I multiply it by 3, what do I get? 3.9. Now we're within a tenth, all right? But if I multiply this, because these are ratios, if I multiply this by 3 and get 3.9 or approximately 4, I have to multiply this one by 3, and that would come out to be 3. So my actual empirical formula will be A3B4. Okay, does that make sense? So it's not the same small number. It's just we don't want to go, oh, well, I can multiply them both by 10 because that's not going to be the smallest ratio, right? That would be what? If I multiply by 10, I'd have A10, B13. Yeah, that doesn't really. What's up?
Mr. Beam, how can you use times 3 there?
Okay, because what we're trying to do is get this number to be within a tenth of a whole number. And that's why I said if we multiply by 2, it would just be 2.6. That's not close enough to round. Yeah.
So we want to get to round up so that we can get a whole number.
Yes, we want a whole number, but we got to be really close to round.
Okay.
Yeah. That's a good question. Thank you for asking that. I'd rather clarify now than confuse everybody. All right? Okay, let's go back over here. Okay, so no, I'm actually going to go here. We're going to do an example, okay? This would be similar to something that might be given in a paper or on a paper because I just actually printed this paper off, stole it from the interwebs. All right, so they do an analysis and they find out that a compound is 63.52% iron and 36.48% sulfur. Okay? And we want to find our empirical formula. Find empirical formula. All right? So, our first step is to find the grams. Well, and since they gave us percentages, we're just going to change that to grams. 63.52 grams of iron and 36.48 grams of sulfur. Okay, the next step was to convert the grams to moles. All right, so if I have grams here, where's it got to go on the next step? To convert it to moles. Huh? On the bottom, right? Where do I find out how many grams go on the bottom? Where's this number going to come from? The formula mass, but it's just for iron, so we don't even have to add it up. We just have to look where? Periodic table, very good. There you go. It's all coming back to you now. All right, and for iron, it's going to be 55.8. Okay, now, we could, since we have 4 significant digits here, we could actually go one more here, but just to keep consistent, we're just going to go to the 10th, and that's going to be 1 mole on top for Fe. All right. For sulfur, I have grams of sulfur here. Where's it going to go on the next step? Bottom. For sulfur, it's 32.1 grams of sulfur, and 1 mole sulfur goes on top. Everybody with me so far? What unit can cancel? The grams, right? I can cancel my grams. So let's cancel that and cancel that. Again, we're only canceling the units. We're not canceling the number. So then we would take 63.5 times 1 divided by 55.8. 63.52, sorry. Divided by 55.8. And so the top number, now on here, keep a little bit more significant digits. If we had 4 here, let's keep 4. So 1.138. And then this one, 36.48 divided by 32.1. Oh, 1.136. Look at this one. They're very close, right? What's the smaller of the two?
Sulfur.
The sulfur. So we divide both sides by sulfur, 136, divided by 1.136. If we divide something by itself, that's going to actually be 1, no matter what, right? On this step, one of them should always come out to be 1. And then we have 1.138 divided by 1.136, and that will equal, oh, look at that, 1.001. Is that close enough I can round it to 1? Yeah. So the empirical formula for this one will just be FES. All right? We don't have to do the multiplying step. I need to do one. So, you remember how we learned? Whoa, where'd my stuff go? Oh, please don't cut out on me when I'm recording. Ah! Oh. I don't, oh, it is still recording. Okay, hold on. I might be able to bring it back. File. Okay, hopefully, oh, it looks like I'm still recording, so we're good. Okay, so all of that stuff we've learned about charges and stuff like that, they actually learned that or figured those out from this raw data. And they were able to figure out the ratio between elements and stuff like that. Give me just a second, and I will come up with a different one. All right. Times, right, and 16. I'm going to come up with one where we have to multiply it out. These are a little trickier because 62 divided by 142. Okay. So we're going to say 43.66% phosphorus and 56.34% oxygen. Okay, we're going to do another one, guys, real quick, or hopefully kind of quickish. All right? So, if we have one like this, all right, and what this does, after they started doing this, they started seeing the patterns between the different elements in the different groups, and that's how they were able to come up with those charges and stuff like that. Go back over that. Okay. All right. So we're going to do the same thing here. They gave us percentages, right? If they give us percentages, the first step is just change it to grams, right? So 43.66 grams P and 56.34 grams of O. Are you with me?
With you.
Yep.
All right. Then our next step is to convert it to what? No, we got the grams. Now we go to moles. So if I have grams of phosphorus here, where's it go on the next step? Bottom. For the periodic table, it's 31 grams of phosphorus is 1 mole of phosphorus. And for oxygen, hopefully you guys have got oxygen kind of memorized by now. Don't you? Yeah, we use oxygen a lot. It's really important. Okay, so we take the 43, 6 divided by 31, and we get 1.408. And that's moles of P. I forgot to write that on the top part. And 56.34 divided by 16 is 3.521 moles of O. All right? Then what was my next step? Divide by? Which one's smallest?
1.408.
Okay, 1.408. So we're going to divide both of them by 1.408. 1.408. Okay, and this one's going to be 1, right? 3.521 divided by 1.408. That one is going to be 2.50. Yeah, that's fine. That's good enough. 2.50. Is 2.5 close enough that I can round it to a whole number? No. What can I multiply that to real simply to get it to a whole number, though? Yeah, I can multiply by 2. So if I take that times 2, what's it going to equal? What's 2.5 times 2? 5. All right. Okay. But whatever I do to this one, I have to do the other one. So
Understand where the 2 came from.
I did.
this here, you're just kind of trying numbers, but we know that 0.5 is half of a 1. So if I multiply by 2, it's going to equal 1, right? Like 0.3 is a third. 0.25 would be, you multiply by 4.
Because the 2 came out of the 2.50.
No, it came just to get 2.50 to 1. Because if I multiply by 1, it's still 2.5. And you just kind of, if you're not sure, you just try. Then I go by 2. If that didn't work, I go by 3. Just keep going by small numbers. Like I said, you could jump to 25, right? Or jump to 10. If I multiply by 10, that'd make it 25. But that would not be the reduced form at that point. Yeah, we want it reduced. So then we're going to multiply this one by 2 as well, because if I do it to one, I got to do it to the other. And so this formula will be P2O5. Does that make sense? Oh, are you kind of with me?
Yeah.
Okay. There is one more step we do with this then to sometimes figure out molecular formula. Again, when we would do this is from raw data. We would, hey, zip it. All right. What we would do is we would do some experiments and we'd get the data and we'd break it down. Sometimes we separate things out. Sometimes we combine them together and we're able to figure out how much of each thing is there. And then we can do it like this, okay? So we can take it to the next step and get to molecular formula, okay? All right, so once we have the empirical formula, finding molecular formula is not bad as long as we know the molecular mass. And that's something else we can determine, all right, from data, okay? Or from experimentation. We can calculate the molecular mass of things, all right? So the molecular formula, also sometimes known as the true formula, shows the total number of each element in a compound, all right? Shows the total number of each element in the compound. Okay, so, what you're gonna need, all right, is gonna be the empirical formula. Sometimes on a problem, they'll give it to you. Sometimes we'll have to calculate it just like we did. All right? Then we're also going to need the empirical mass. All right? The empirical mass is just the formula mass of the empirical formula. Again, they might give it to you. I kind of doubt it most times. Or you'll have to calculate it, but it's just like we've been doing where you add it up. Just you add it up for the empirical formula. All right? Then you have to know the molecular mass. This can be found experimentally, but for our practice stuff on worksheets and stuff, they will always give the molecular mass to you. All right, all right, all right? Yes, Mr. Beeman. Okay, good. As long as we're all there. All right, go ahead and write that down. And then you'll use a simple little calculation. Now, there is a little bit different way you can do it as long as you're given percentages, but I have found it's more confusing to teach the second method than it is just to do it this way. Because this way, we're always using the same method. Okay? Mm-hmm. Are we still writing or are we good? Still writing? Okay. Right. Well, we're going to, as soon as we get done with this, then the rest of the time you'll be working on practice problems. So,
This slide or like.
yeah, this slide, well, we're going to do a practice doing this. All right. The very last part of this, guys, is the actual formula. Okay. So, to find the molecular formula, what you're going to do is take the the molecular mass, divided by the empirical mass, and then you multiply it by the subscripts of the empirical formula, but I just put the empirical formula there, EF. So those are just molecular mass divided by empirical mass times the empirical formula. All right, all right, all right? And if you can, and I think, I may even put that on the quiz, just put that formula there. If you know how to use it, you'll be good. All right? I don't know. I might not. I probably will. I'm feeling nice. Okay, you guys ready to do an example?
Yes.
Okay, so one of the things, all right, so let me, first of all, they tell us in an experiment, we find out that a compound is 0.606 grams of nitrogen and 1.390 grams of O. It is also determined to have a molecular mass of 92 grams per mole, okay, for the whole molecule. So what we need to do is find the empirical and molecular formula. Okay? Can you guys read that? Sorry, I was kind of scribbly. Okay, whenever I'm doing one that requires molecular formula, all right, what I will do is put down the EF for empirical formula, because I know I'm going to have that. I'm going to put down the molecular mass. I'm going to put down the empirical mass. I put it in that order because it helps me set up my problem. And then I put down the molecular formula, which is ultimately what I'm looking for.
What's the EF stand for?
EF stands for empirical formula. Okay? And the molecular mass they gave us was 92 grams per mole. Everything else we're going to have to figure out. Now, this time they didn't give us percentages, they just gave us grams. So we start with that, 0.606 grams of nitrogen and 1.390 grams of O. we have to convert it to what first to get our empirical formula? Moles. So if I have grams of nitrogen here, where's it go in the next step? Bottom of periodic table, it's 14 grams of N is 1 mole of N. And what's the mass for oxygen? 16, good. Grams of O is 1 mole of O. Then we use our handy dandy calculadora, 0.606. Oh, helps if I actually hit the right buttons. 06 divided by 14, and we get a really small number, 0.04329, and that's moles N. And 1.390 divided by 16.0, and this one comes out to 0.08687, actually 88, I guess. All right, and that's moles of N, or of O, sorry, moles O. Okay, so what's my next step? Divide by what?
0.043.
Yep, 0.043, or divide by the smallest. All right, so we're going to divide both of them by 0.04329, 0.04329. All right, so what's the top one going to come out to be? 1. What's the bottom one going to come out to be? 0.04329. It comes out to be 2.0007, so that's close enough. I can round it to 2. So my empirical formula will just be NO2. Oop, there we go. Does that make sense? We're good with that. That's the third example we've done of that. Now, to get to the molecular formula, we're going to take the NO2. We got to add it up. How many N's are there? 1. How many O's? 2. And then times their mass again, 14 and 16. And so that's 14, and that's 32. So total of 46. So my empirical mass, is 46 grams. So then we use our equation. What equation? This bottom one, MM divided by EM times EF. So what does that mean? Other way, 92 divided by 46 times NO2. All right, what's 92 divided by 46 going to be? 2. All right, so this altogether comes out to be 2. When I multiply it by each subscript. So the molecular formula for this compound will be N2O4. And if we want to do even a little bit of review, that would be dinitrogen tetroxide. Okay? That's not too bad, is it? It's pretty bad.
I understand it, but like it's gonna be a lot to remember all the steps perfectly.
But yeah, and we're going to go through them. You're going to get some practice, okay? I'm going to, any clarification questions before I stop the video?
Wait, I'm confused with the last part where you get like 92 divided by 46. Like I get that, and then the answer is 2.
Yes.
And then how do you put that on the NO2?
So when we multiply, so in my equation, I just made it real simple so it's easy to remember. I say multiply by the empirical formula. So what you're just doing is you're taking that number and multiply it by the subscripts of the empirical formula. Okay, not the whole thing. All right? Does that make sense? Okay, let me pause the video. Shift 5. And stop.